66 million years ago, the sky changed. An asteroid struck Earth, and the age of the dinosaurs came to an end. That is where most stories stop. But the world that followed was not a quiet recovery. It was an experiment that lasted tens of millions of years, an era that built the planet we now recognize. Mountain ranges rose high enough to alter global wind patterns. Antarctica drifted into isolation and froze. Ocean currents reorganized into systems that still regulate climate today. Grasslands appeared for the first time. Mammals expanded into forms no ecosystem had seen before. Whales returned to the sea. Human ancestors appeared only in the final fraction of this immense stretch of time. This was the Cenozoic. It did not unfold gently. The early part of the era was warmer than today, with tropical forests reaching into polar regions. Later, the planet cooled step by step until ice sheets advanced and retreated in repeated cycles. Sea levels rose and fell by hundreds of feet. Ecosystems reorganized again and again. We often call it the age of mammals, as though it were stable, but was it ever steady at all? What did it take for climates, oceans, and continents to settle into something humans could survive? Why did stability emerge only after repeated swings between warmth and ice? And if this era shaped almost everything around us, how secure is that stability now? Tonight, we step into the Cenozoic, not as a simple aftermath, but as the long, restless era that shaped everything familiar around us. But before we begin, I'd love to know, where in the world are you listening from tonight, and what time is it there? Your comments are one of my favorite parts of this sleepy little community. And if you're enjoying these gentle journeys, a like or subscribe truly helps this calm corner of science keep growing. Now take a slow breath, let your shoulders loosen, and together, let's move into the era that built the modern Earth. The sky cleared long before life understood what had happened. Dust that once veiled the sun thinned gradually, allowing a pale light to return to landscapes stripped of their former rulers. Forests stood broken and silent, their canopies torn open, their great reptilian inhabitants gone. Across oceans and continents, nearly three-quarters of living species had vanished in a geological instant. Coral reefs collapsed into rubble. Ammonites that had drifted through ancient seas for millions of years disappeared entirely. On land, the immense bodies that once pressed footprints into floodplains were no longer there to cast their shadows. What remained was smaller, quieter, and largely hidden. Mammals that had survived the catastrophe were creatures of modest size, many no larger than modern rodents. For millions of years they had lived in the margins, emerging mostly at night, feeding on insects, seeds, and scraps beneath the dominance of dinosaurs. Their bones were light, their teeth generalized, their metabolism steady and warm. They endured not because they were powerful, but because they were flexible. In burrows and under fallen trunks, they waded through the long darkness that followed impact. The first centuries of recovery were uneven. Wildfires had swept across continents, leaving charcoal embedded within sedimentary layers that would later harden into stone. Yet spores and hardy plants returned quickly, spreading across ash-covered ground. Pollen grains preserved in ancient rock reveal this quiet resurgence. Ferns expanded in abundance, forming what paleobotanists call a fern spike, a brief dominance recorded in microscopic detail. Gradually, flowering plants reclaimed river valleys and uplands, rebuilding layered forests from the soil upward. The structure of ecosystems began to knit itself back together, not as a replica of what had been, but as something altered. With the great herbivores gone, vegetation thickened in places once kept open by constant grazing. Rivers shifted through newly vegetated floodplains. Insects diversified alongside flowering plants, renewing intricate partnerships. The absence of giants created ecological vacancies across every environment. There were no massive predators to patrol coastal swamps, no towering browsers to strip leaves from high branches. Space existed where once there had been competition. Within that space, mammals began to experiment. Subtle changes in tooth shape and limb structure appear in fossil beds dated to the early Paleocene. Some species grew slightly larger, others adapted to climb, to dig, or to swim. The world was still unstable, climates fluctuating as atmospheric systems rebalanced, yet opportunity persisted. Over tens of thousands of years, then hundreds of thousands, ecosystems stabilized into new configurations. The Paleocene opened not with grandeur, but with resilience, as life assembled itself from survivors into a planet no longer ruled by giants, yet quietly preparing for expansion. In the layers of stone, laid down after the silence, bones begin to multiply. They appear first as scattered fragments in river sediments, then as fuller skeletons preserved in ancient floodplains, subtle signals that life was no longer merely surviving but unfolding. Across what is now North America and Europe, early Paleocene and Eocene deposits hold an increasing variety of small mammalian forms. Jaw shapes diversify, teeth specialize, limbs lengthen or compress. Evolution, once constrained to the margins, begins to explore open ground. The transformation is not sudden in appearance, yet its pace is unmistakable in geological terms. Within a few million years, lineages branch repeatedly. Some mammals grow into sturdy herbivores with grinding molars suited to leaves and shoots, their bodies expanding beyond the diminutive sizes of their ancestors. Others sharpen their teeth into slicing crests, adapting to diets of flesh and bone. The rebuilding of predator and prey relationships introduces motion back into ecosystems, a balancing rhythm shaped by pursuit and evasion. Hoofed mammals, early ungulates, spread through forest understories and along wetlands, their weight supported by evolving limb structures that favor endurance over concealment. In certain fossil beds of the Bighorn Basin and the Paris Basin, paleontologists have uncovered a tapestry of this diversification. Skeletons lie in layered sediments that once bordered subtropical rivers. There, small arboreal mammals with grasping digits hint at a new ecological experiment. These early primates possess forward-facing eyes and flexible shoulders, features that suggest movement through branches rather than across open ground. Their emergence reflects a forest canopy regaining complexity, where depth perception and balance become evolutionary currency. Vision sharpens, hands become more precise. Neural pathways expand subtly to coordinate these changes. Climate during this interval trends warmer, encouraging lush vegetation across high latitudes. Broadleaf forests extend into regions that would later cool dramatically. In these dense habitats, mammalian forms continue to diverge. Some species approach the mass of modern tapirs, browsing on abundant foliage. Others remain small and swift, exploiting insects and fruits. With dinosaurs absent, ecological niches once unreachable now invite occupation. Body plans respond accordingly, experimenting with size, posture, and diet in combinations not previously possible. Predation intensifies as carnivorous mammals refine their senses. Auditory structures improve, olfactory bulbs enlarge, and limb proportions shift toward agility. The fossil record captures tooth marks on bone and healed fractures, silent evidence of encounters survived. This interplay stabilizes communities through pressure and adaptation, establishing feedback loops that regulate abundance. Diversity itself becomes a form of resilience, buffering ecosystems against localized disturbance. By the close of this early expansion, mammals occupy nearly every terrestrial habitat available to them, from forest floor to canopy, from river margin to inland plain. Their presence is etched into sedimentary archives. The world that had once belonged to towering reptiles now hums with smaller, fur covered bodies whose variety grows with each passing epoch, quietly shaping the direction of the age. Mass leaves an imprint long before it becomes bone. In sediments dating deeper into the Eocene, trackways widen, stride lengths stretch, and the architecture of skeletons begins to change in proportion. What had once been modest bodies now lengthen and thicken, vertebrae stacking beneath heavier muscle, limb bones reinforcing under increased load. The world, warm and generously vegetated, supports this enlargement. Energy flows steadily through dense plant growth, and herbivorous mammals respond by scaling upward, their digestive systems expanding to process fibrous leaves and shoots with greater efficiency. Among these enlarging forms rise the early perissodactyls and artiodactyls, hoofed mammals whose toes consolidate into supportive columns. Ankles stiffen, allowing longer travel across soft floodplains and forest clearings. Their teeth evolve higher crowns and complex ridges, built to grind abrasive vegetation that carries microscopic grit. In fossil assemblages from Wyoming to Western Europe, skulls of these herbivores grow progressively broader, nasal passages deepening, jaws strengthening. Some approach the mass of modern rhinoceroses, though their features remain experimental, proportions not yet fixed by later refinement. Predators expand alongside them. Creodonts and early carnivoromorphs lengthen their limbs and sharpen their dentition, developing slicing carnassial teeth capable of shearing flesh with precision. Shoulder blades loosen to allow greater stride extension. Claws curve more decisively. As prey grows larger, hunters follow, and the equilibrium between pursuit and escape intensifies. Bite marks etched into fossilized bone record these encounters without drama, only evidence of energy transferred from one body to another. Not all dominance in this interval belongs to mammals. In parts of South America and elsewhere, giant flightless birds step into apex roles. Their beaks curve like blades, necks tall and muscular, legs built for speed across open terrain. These terror birds, as they are sometimes called, occupy ecological positions once held by large reptilian predators. Their skeletons suggest keen vision and forceful strikes, a different lineage claiming stature in a world recalibrating its hierarchy. Body size during this era correlates subtly with atmospheric and climatic conditions. Elevated global temperatures reduce polar ice and expand habitable zones, while atmospheric oxygen levels, though not dramatically higher than today, remain sufficient to sustain large, active animals. Warmth extends growing seasons, increasing primary productivity. In such environments, larger bodies retain heat efficiently and traverse longer distances in search of food. Yet size also demands stability. Fluctuations in climate will later test these giants, selecting again for adaptability. By the close of this phase, mammals occupy a spectrum of mass unimaginable in their earlier, concealed existence. Some remain small and agile, threading through undergrowth. Others tower above shrubs, their silhouettes reshaping horizons. The age that began with survivors in shadow now hosts creatures of substantial presence, their weight pressing into soil that continues to record the slow accumulation of change. Deep within marine sediments, a thin band of altered chemistry marks a turning point. It is not visible as flame or ash, but as a subtle shift in carbon isotopes, a signature left by a rapid infusion of greenhouse gases into the atmosphere. This interval, known as the Paleocene-Eocene thermal maximum, unfolds over only a few thousand years, swift in geological terms, and it transforms the planet with quiet intensity. Carbon, long stored in oceanic hydrates and organic deposits, enters the air and sea in extraordinary volume. The ratio of lighter carbon isotopes increases abruptly in sediment cores recovered from the Atlantic and Pacific, evidence that ancient carbon reservoirs destabilized. Volcanic activity associated with the opening of the North Atlantic may have contributed, heating sediments and releasing methane. Whatever the precise trigger, the outcome is clear in the rock record. Global temperatures climb by several degrees Celsius, estimates ranging between 5 and 8, reshaping climate systems across continents. Forests expand toward higher latitudes, and subtropical conditions extend far beyond their earlier boundaries. In regions that would one day host temperate climates, palms and broadleaf evergreens flourish. Rainfall patterns intensify in some areas, while interior zones experience alternating wet and dry intervals. The hydrological cycle accelerates, carrying warmth poleward through atmospheric circulation. Polar regions, already mild compared with later epochs, become even more temperate, reducing the gradient between equator and pole. The oceans absorb a significant portion of the excess carbon dioxide, and in doing so, their chemistry shifts. Seawater becomes more acidic, dissolving calcium carbonate shells on the seafloor. In deep marine cores, layers rich in microfossils thin or disappear, replaced by clay, where once there had been abundant foraminifera. This dissolution horizon records a biological strain that reverberates through marine food webs. Some benthic species vanish entirely, while others adapt to altered conditions. Surface waters warm, affecting plankton communities that form the base of oceanic ecosystems. On land, mammals respond to rising temperatures in subtle ways. Fossil evidence indicates a temporary reduction in body size among several lineages, a pattern consistent with Bergmann's rule, where smaller forms dissipate heat more efficiently in warmer climates. At the same time, many species migrate poleward, tracking suitable habitats as thermal zones shift. Plant communities move in tandem, seeds dispersing into newly hospitable regions. The distribution of life becomes fluid, contours of biodiversity sliding gradually across latitudes. This warming episode does not persist indefinitely. Over tens of thousands of years, weathering of silicate rocks increases under higher rainfall, drawing carbon dioxide from the atmosphere and storing it in carbonate minerals. Gradually, temperatures moderate, yet the imprint of the Paleocene-Eocene thermal maximum remains etched in stone, a reminder that Earth's climate system can pivot rapidly when carbon cycles are disrupted, altering oceans, continents, and the pathways of evolution in a single, sustained surge of heat. Far from the equator, in lands that now know months of darkness and fields of ice, stone holds the memory of leaves. Impressions of broad fronds lie pressed within sediment that once formed on floodplains near the Arctic Circle. Among them are the unmistakable outlines of palm foliage, their veins radiating outward in patterns associated with warmth and abundant rainfall. These fossils do not speak of brief seasonal anomalies, but of sustained climates capable of supporting forests where winter today would freeze soil to bedrock. During the early and middle intervals of this warm epoch, polar regions were not sealed beneath permanent ice. Instead, they hosted dense vegetation shaped by extended daylight in summer and muted twilight in winter. Growth rings in fossilized wood recovered from high latitudes reveal rapid seasonal expansion, followed by slower periods of dormancy, yet not the severe contraction that freezing conditions impose. The absence of glacial deposits from these layers confirms what the flora suggests. Ice sheets had not yet claimed these continents as their own. Antarctica, now defined by wind and white horizons, once supported temperate rainforests along its coasts and interior valleys. Fossil trunks, petrified in place, indicate stands of southern beech and conifer species adapted to mild conditions. Leaf assemblages, preserved in sedimentary basins, show diversity comparable to modern temperate forests in parts of New Zealand or southern South America. Rivers flowed through landscapes lined with vegetation, carrying organic material into shallow seas where it settled into accumulating strata. Animal life mirrored this botanical richness. Remains of reptilian lineages, including relatives of crocodiles, have been discovered in sediments formed at latitudes that today lie well within the Arctic Circle. These creatures, dependent on relatively warm water for thermoregulation, could not have survived prolonged freezing. Their presence implies winter temperatures that remained above lethal thresholds, supported by atmospheric carbon dioxide concentrations higher than those of later epochs. The gradient between equator and pole was reduced, distributing heat more evenly across the globe. Ocean circulation patterns during this time differed from those that would later isolate Antarctica thermally. Without a fully developed circumpolar current to encircle the southern continent, warm waters penetrated higher latitudes, moderating coastal climates. Continental configurations allowed different pathways for currents, redistributing energy through basins that were still adjusting their connections. In this arrangement, polar amplification operated not as a harbinger of ice, but as an extension of warmth. The geological record preserves these conditions with remarkable clarity. Pollen grains extracted from Arctic cores match species associated with subtropical and temperate ecosystems. Isotopic analyses of fossil shells corroborate elevated sea surface temperatures at high latitudes. Together, these lines of evidence depict a planet whose poles were forested and biologically active, a configuration sustained for millions of years before tectonic shifts and atmospheric changes initiated a gradual descent toward cooler states. Along the margins of an ancient sea that once covered parts of what is now Pakistan, a small hoofed mammal moved through river shallows, its body balanced between two worlds. The sediments that entombed it would harden into rock and, millions of years later, reveal a skull unlike any other. This creature, known as Pakicetus, possessed teeth shaped like those of terrestrial carnivores, yet its ear region held a distinctive thickened bone called the involucrum, a structure now recognized as uniquely cetacean. In that dense bone lay the earliest signal of a lineage beginning to lean toward water. Pakicetus still walked on four legs, its limbs proportioned for land, its spine flexible enough for running. Isotopic analysis of its teeth suggests that it fed partly in aquatic settings, perhaps ambushing prey along riverbanks. From such beginnings, a gradual transformation unfolded. Later forms, including Ambulocetus, show elongated bodies and more robust tails, their hind limbs powerful for paddling while still capable of bearing weight on land. The pelvis begins to loosen its tight articulation with the spine, allowing greater undulation through the torso. Feet broaden, digits lengthen, and webbing likely stretched between them. As millions of years passed, vertebrae modified to support a stronger up and down motion of the spine, the foundation of the swimming stroke that would define whales. Nostrils migrated slightly backward along the snout in successive species, an incremental repositioning that would eventually culminate in the blowhole atop the head. Hind limbs reduced in size, their bones shrinking generation by generation until they became internal vestiges, no longer functional for walking. The forelimbs transformed into flippers, with elongated finger bones encased in connective tissue, forming rigid paddles suited for steering rather than grasping. This transition unfolded within warm Eocene seas, rich in fish and invertebrates. As bodies adapted to buoyancy and propulsion, sensory systems evolved in parallel. The ear bones became increasingly specialized for underwater hearing, isolated from the skull by air-filled sinuses that enhanced directional perception. In toothed whales, echolocation emerged as a refined biological sonar. Nasal passages and associated soft tissues reorganized to produce focused sound pulses, which traveled through water, reflected off objects, and returned as echoes interpreted by an enlarged auditory cortex. This innovation allowed navigation and hunting in murky depths where vision faltered. Fossil sites across South Asia, North Africa, and North America preserve intermediate forms that document this progression with unusual clarity. Each skeleton captures a moment in anatomical negotiation between gravity and buoyancy. Over roughly 10 million years, descendants of small terrestrial mammals committed fully to marine life, relinquishing their dependence on land. By the close of this transformation, early whales, such as Basilosaurus, reached lengths exceeding those of many modern species, their serpentine bodies gliding through coastal waters that once bordered continents still reshaping. At the far southern edge of the planet, continents once nearly touching began to part by increments too slow for any living creature to perceive. South America drifted westward, Antarctica edged into greater isolation, and between them, a seaway gradually widened. This opening, known today as the Drake Passage, did not appear in a single rupture, but through persistent tectonic motion. Plate boundaries stretching and thinning until deep water could flow uninterrupted around the southern continent. As the gap deepened and broadened, ocean circulation reorganized on a planetary scale. Warm currents that had once reached Antarctic shores were diverted. In their place, a powerful eastward flowing system emerged, encircling the continent without obstruction. This was the beginning of the Antarctic Circumpolar Current, the strongest continuous current on Earth. Driven by prevailing westerly winds and unimpeded by land, it formed a thermal barrier that limited the exchange of warmer equatorial waters with the high southern latitudes. The consequences unfolded gradually, yet decisively. Surface waters around Antarctica cooled as heat transport diminished. Seasonal sea ice began to form more extensively, increasing the reflectivity of the region and reinforcing further cooling through feedback loops. Cold, dense water sank near the continent, contributing to deep ocean circulation patterns that extended into global basins. The isolation of Antarctica became not only geographic, but climatic, its ecosystems responding to a steadily lowering temperature regime. Sediment cores recovered from the Southern Ocean record this transition with clarity. Microfossils shift in composition, reflecting cooler water species replacing those adapted to warmth. Oxygen isotope ratios in marine shells indicate a decline in global temperatures and the growth of continental ice. Glacial deposits appear in Antarctic strata, marking the establishment of ice sheets that would, in time, thicken and spread across much of the continent. The transformation was not abrupt, but it set the direction for the remainder of the era. This reorganization of ocean currents influenced climates far beyond the southern hemisphere. By strengthening the thermal contrast between equator and pole, the Antarctic Circumpolar Current altered atmospheric circulation patterns, contributing to changes in precipitation and temperature distribution across continents. The deep ocean became more stratified in places, nutrient flows shifting as cold waters circulated through abyssal plains. Carbon exchange between ocean and atmosphere adjusted in response, linking tectonic motion to long-term climate regulation. With Antarctica increasingly encased in ice, the planet entered a prolonged cooling trajectory. Forests that once bordered southern shores retreated. Marine communities adapted to colder, more seasonal conditions. The birth of this circumpolar current did not end warmth everywhere, yet it marked a structural pivot in Earth's climate system, anchoring a pattern of cooling that would shape subsequent millions of years and redefine the character of global oceans. Across continents that had long been dominated by layered forests, a quieter botanical shift began to spread from river margins and disturbed ground. Low-growing plants with narrow leaves and basal growth points gradually extended their reach, forming patches that shimmered under open sky. These were early grasses, members of a lineage that had existed in modest numbers for millions of years, yet now found expanding opportunity as climates cooled and dried in certain regions. Their architecture differed from that of broadleaf plants. Growth emerged from the base rather than the tip, allowing recovery after fire, trampling, or grazing. Within each blade, microscopic bodies of silica accumulated in specialized cells. These phytoliths hardened the tissue, giving grasses a subtle abrasiveness. To the touch, they felt supple, yet to the teeth of herbivores, they introduced resistance. As grasslands widened, mammals feeding upon them faced new mechanical demands. Molars elongated and developed higher crowns, a condition known as hypsodonty, enabling animals to endure the constant wear imposed by silica-rich vegetation and the grit carried by wind across open plains. Tooth enamel thickened, jaws strengthened, and chewing motions adjusted to grind fibrous stems efficiently. This exchange between plant and grazer unfolded gradually, each influencing the evolutionary path of the other. Herds of early horses, antelope relatives, and other ungulates began to frequent expanding clearings, their limbs lengthening to support sustained movement over distance. Hooves became more specialized for firm ground rather than soft forest floor. As grazing intensified, grasses responded by spreading through rhizomes and seeds adapted for wind dispersal, reinforcing dominance across broad landscapes. Fire, ignited naturally by lightning, further favored these ecosystems. Grasses regenerated quickly after burning, while many woody plants struggled to reclaim territory. Sedimentary records reveal a corresponding increase in grass pollen and distinctive carbon isotope signatures associated with open habitat vegetation. In regions of North America, Africa, and parts of Asia, fossil soils, known as paleosols, document the transition from forested conditions to more arid, grassy environments. Dust deposition increased as vegetation structure changed, altering albedo and influencing regional climate patterns. The rise of grasslands was not uniform across the globe, yet where conditions permitted, these ecosystems reshaped entire continents. Open habitats encouraged new behaviors among animals. Visual range extended across unobstructed terrain, favoring heightened eyesight and social grouping as defense against predators. Carnivores adapted in turn, developing speed and endurance to pursue prey over distance. Energy flow through these systems differed from that of forests, with large herbivore biomass supporting intricate food webs. What began as scattered stands of resilient plants evolved into sweeping savannas and prairies that would one day sustain immense herds and, much later, Human agriculture. The spread of grasses represented more than a botanical adjustment. It marked a reorganization of land, climate feedbacks, and evolutionary pressures, weaving open sky into the fabric of the age. Claws leave different signatures than hooves. In Miocene and Pliocene deposits across the Americas, the marks of pursuit begin to sharpen in both bone and landscape. Predators diversify alongside the open habitats and complex food webs that now stretch across continents. Flesh becomes a primary currency in ecosystems shaped by speed, coordination, and calculated ambush. Among the most striking of these hunters are the saber-toothed cats, members of lineages such as Smilodon and its relatives. Their elongated upper canines curve downward like polished ivory blades, supported by powerful neck muscles and reinforced forelimbs. Unlike modern big cats that rely on suffocation through throat bites, these predators likely employed precision strikes to soft tissue, using strength to restrain prey before delivering controlled wounds. Fossil assemblages in regions such as La Brea reveal individuals with healed injuries, suggesting social behavior or at least tolerance among group members during feeding. Their bodies were compact, yet immensely muscular, built for grappling rather than prolonged chases. South America, long isolated before its eventual connection to the north, fostered its own apex predators. Giant flightless birds, descendants of earlier avian lineages, dominated certain landscapes. Often called terror birds, these creatures possessed hooked beaks capable of delivering forceful blows. Their long legs indicate agility across open terrain, and their skull morphology suggests acute vision. In ecosystems where mammalian carnivores were initially scarce, these birds occupied the highest trophic levels, shaping prey populations through direct predation and behavioral pressure. Meanwhile, another lineage, known colloquially as bear dogs or amphicyonids, spread across parts of North America and Eurasia. These animals combined traits seen in both bears and canids, though they belonged to a distinct family. Some species reached impressive sizes, with robust limbs and formidable jaws suited to crushing bone. Their dental patterns indicate dietary flexibility, ranging from active predation to scavenging. In certain environments, they competed directly with early true dogs and other carnivorous mammals, contributing to dynamic shifts in predator hierarchies. Hunting strategies during this interval diversified in response to evolving prey defenses. As ungulates developed heightened speed and herding behaviors, predators adapted with coordinated attacks, stealth approaches, or bursts of acceleration. Limb proportions change subtly, with cursorial species elongating distal segments to maximize stride efficiency. Sensory systems refined further, particularly in vision and hearing, enabling detection of movement across wide grasslands or within fragmented woodlands. The fossil record captures these interactions not only in skeletons but in trace evidence. Tooth punctures align with bite force estimates, and trackways reveal moments of chase preserved in hardened sediment. Each adaptation reflects an ongoing dialogue between predator and prey, a feedback loop driving anatomical innovation on both sides. The New World became a theater of experimentation in carnivory, where birds, cats, and bear dogs each tested different solutions to the challenge of securing energy in a landscape increasingly defined by openness and motion. Far to the south of the equator, a continental fragment once moved in quiet persistence across the Tethyan waters, closing distance measured not in years but in millions of them. The Indian Plate, having separated long before from Gondwanan lands, advanced northward at remarkable speed for tectonic motion. Beneath the surface, oceanic crust subducted and vanished, narrowing the sea that had long divided it from Asia. Eventually, the intervening basin thinned to nothing, and continental edges met with a force that neither could easily absorb. When buoyant continental crust encounters its equal, it does not sink readily into the mantle. Instead, it compresses, buckles, and thickens. Sediments, once laid down in warm marine shallows, were thrust upward, folded into rising ridges. Marine limestones climbed skyward, carrying within them the shells of organisms that had lived far below sea level. From this prolonged collision emerged the early Himalayas, a mountain system that would continue to grow as convergence persisted. The uplift was not instantaneous but cumulative, each increment of compression adding height and altering atmospheric circulation. As elevations increased, so did the exposure of fresh rock to wind and rain. Chemical weathering intensified along steep slopes and monsoon-drenched valleys. Silicate minerals, when broken down in the presence of carbon dioxide and water, form bicarbonate ions that are carried by rivers to the oceans, where they eventually contribute to carbonate sediment formation. In this way, the rise of mountains enhances the long-term removal of carbon dioxide from the atmosphere. The Himalayas and the Tibetan Plateau together created vast surfaces for such reactions, linking tectonic uplift to global carbon cycles. River systems reorganized in response to the new topography. Sediment loads increased, depositing thick layers downstream and reshaping lowland basins. The growing plateau altered wind patterns, strengthening seasonal monsoons that further amplified weathering processes. With more carbon dioxide drawn from the air and locked into marine sediments, atmospheric concentrations gradually declined. This reduction did not cool the planet overnight, yet over millions of years it contributed to a persistent downward trend in global temperatures. Isotopic data from marine cores reflect this transition, showing shifts consistent with expanding ice and cooling seas. The collision between India and Asia thus became more than a regional geological event. It marked a structural pivot in Earth's climate system, coupling mountain building with atmospheric chemistry. As the Himalayas continued their ascent, glaciers would eventually crown their peaks, and the broader planet would feel the consequences. The slow grinding of continental plates had set in motion a feedback that favored a cooler world, redirecting the trajectory of the era toward conditions that would shape ecosystems and, much later, the environments inhabited by humans. White does not arrive all at once. It begins as seasonal persistence, snow that lingers through summer on high ground, compacting year after year into fern, then into glacial ice. As the southern continent continued its slow isolation and atmospheric carbon dioxide declined through intensified weathering, temperatures crossed thresholds that allowed ice to remain. What had once been a landscape of temperate forests and flowing rivers gradually yielded to a spreading mantle of frozen accumulation. The earliest large Antarctic ice sheets formed during the transition into the Oligocene, when cooling reached a point that sustained continental-scale glaciation. Snowfields expanded outward from elevated interiors, coalescing into thick bodies of ice that pressed under their own weight. As glaciers advanced toward the coast, they scoured bedrock, carving basins and transporting sediment into surrounding seas. The growth of ice altered the albedo of the continent, reflecting greater amounts of solar radiation and reinforcing further cooling in a self-amplifying cycle. Marine sediments encircling Antarctica record this transformation with layered precision. Cores extracted from the Southern Ocean reveal a shift from microfossils associated with warmer waters to assemblages adapted to colder conditions. Dropstones appear within fine-grained deposits, isolated rocks released from melting icebergs that had carried them far from their source. Oxygen isotope ratios in foraminifera shells indicate both cooling ocean temperatures and the sequestration of vast quantities of water in continental ice. These chemical signatures align with the timing of glacial expansion, providing converging lines of evidence for the onset of a new climatic regime. As water became locked within ice sheets, global sea levels fell. Shorelines migrated seaward, exposing continental shelves that had previously lain beneath shallow seas. Coastal ecosystems adjusted to changing salinity and temperature gradients, while terrestrial corridors emerged in regions where lowered seas connected landmasses intermittently. The redistribution of water mass also influenced Earth's crust, causing subtle isostatic responses as the weight of ice depressed Antarctic lithosphere. The establishment of major Antarctic ice sheets marked a decisive shift from greenhouse conditions toward an icehouse world. Seasonal contrasts sharpened, and the thermal gradient between equator and pole increased. Ocean circulation patterns adapted to colder southern waters, strengthening deep water formation and influencing nutrient transport across basins. Climate variability did not vanish, yet the baseline state of the planet had changed. Ice became a persistent presence, shaping atmospheric dynamics and planetary energy balance for millions of years to follow. In this frozen transformation, the southern continent assumed a new role within Earth's system. Its reflective surface and circulating currents anchored a cooler trajectory, guiding the remainder of the era through alternating pulses of glaciation and retreat. The quiet accumulation of snow had matured into a defining feature of global climate, establishing conditions that would reverberate across every latitude. A narrow ribbon of land rose slowly between two vast oceans, built not in a moment of upheaval, but through the steady uplift of volcanic arcs and the accumulation of sediment. Where open water had once allowed uninterrupted exchange between the Atlantic and Pacific, a barrier began to form. This emerging bridge, the Isthmus of Panama, linked North and South America after tens of millions of years of separation. Its completion reshaped currents, climates, and the trajectories of countless species. Before this connection, South America had evolved in relative isolation, its ecosystems shaped by marsupial predators, giant flightless birds, and unique herbivores unlike those elsewhere. North America, by contrast, hosted placental mammals that had diversified under different pressures. When the land corridor solidified, migration unfolded gradually yet decisively. Armadillos, ground sloths, and opossums moved northward, entering new habitats and climates. From the north came cats, canids, bears, and hoofed mammals, crossing into southern territories where their evolutionary histories had never intersected. The exchange did not produce equal outcomes for all participants. In many regions of South America, incoming northern predators proved formidable competitors. Fossil records reveal declines and extinctions among certain native carnivores and herbivores following the arrival of placental lineages. Yet the interchange was not a simple replacement. Some southern migrants established enduring populations in the north, adapting successfully to varied environments. The mixing generated novel communities, altering food webs and reshaping ecological balances across both continents. Sedimentary sequences capture this transition with layers containing mixed faunal assemblages, species once separated now appearing side by side. Teeth, limb bones, and skull fragments testify to overlapping ranges and shifting dominance. Competition intensified where niches overlapped, driving selective pressures that refined speed endurance, and defensive strategies. In this merging of biotas, evolution accelerated under new interactions, testing resilience against unfamiliar rivals and climates. Beyond terrestrial consequences, the closure of the seaway influenced ocean circulation profoundly. With Atlantic and Pacific waters no longer freely mingling at low latitudes, salinity gradients changed. The Atlantic became saltier, enhancing the formation of dense, sinking waters in the North Atlantic. This strengthened components of the global thermohaline circulation, contributing to increased heat transport toward higher northern latitudes. Such changes are linked to climatic shifts that encouraged further cooling and the expansion of northern hemisphere ice sheets in later epochs. Thus, the rise of a slender land bridge accomplished more than a geographic union. It reconfigured atmospheric and oceanic patterns while orchestrating one of the most significant faunal exchanges in the history of mammals. Continents, once divided by open sea, now shared species, competitors, and climatic influences. The Earth's surface, in continuing motion, had redrawn boundaries, and life responded by moving, adapting, and, in some cases, fading into the fossil record as new ecological arrangements took hold. Light began to organize the land in new ways. As climates oscillated and continental interiors experienced increasing seasonality, mosaics of open grass and scattered trees expanded across broad regions. Savannas emerged where rainfall was sufficient to support woody plants, yet periodic drought and fire limited dense canopy closure. In these transitional zones, grasses and acacias shared space beneath wide skies, creating habitats structured by both exposure and shelter. Herbivores adapted to this patchwork, moved between shade and sun, shaping vegetation through browsing and grazing that reinforced the balance between tree and grass. Forests did not vanish, but they reorganized. In some equatorial regions, rainforests persisted with layered complexity, yet even there species composition shifted as temperature and precipitation patterns changed. In temperate zones, deciduous trees expanded, shedding leaves in response to cooler seasons and conserving resources during periods of reduced light. Coniferous forests gained prominence in higher latitudes, their needle-like leaves better suited to colder conditions and shorter growing seasons. Plant communities became increasingly attuned to climatic gradients, arranging themselves in belts that mirrored atmospheric circulation. Along tropical coastlines, shallow seas fostered the growth of coral reefs whose structures resemble living architecture. Reef-building corals, hosting symbiotic algae within their tissues, deposited calcium carbonate skeletons that accumulated into vast frameworks. These formations provided habitat for fish, mollusks, and countless invertebrates, enhancing marine biodiversity. As sea levels fluctuated with the waxing and waning of ice, reefs advanced or retreated, adapting to changing shorelines. The clarity and warmth of tropical waters supported this expansion, linking ocean chemistry and sunlight to the construction of intricate ecosystems. Within flowering plants, relationships with insects deepened. Pollinators diversified alongside angiosperms, forming mutualistic partnerships that accelerated reproductive success. Bees evolved specialized mouthparts and behaviors for collecting nectar and pollen, while butterflies and moths developed elongated proboscises to access tubular blossoms. The timing of flowering synchronized with insect life cycles, creating seasonal rhythms of color and movement across landscapes. These interactions increased genetic exchange among plant populations, fostering resilience and adaptability in fluctuating climates. The spread of modern ecosystems did not occur uniformly, yet over millions of years recognizable patterns took shape. Savannas supported herds, and predators adapted to open terrain. Forests stratified according to latitude and altitude. Coral reefs fringed warm coasts with biodiverse communities. Pollination networks wove connections between plant and insect, amplifying ecological complexity. Each system responded to tectonic shifts, atmospheric changes, and evolutionary innovation, forming the foundations of habitats that persist in altered forms today. Through gradual reconfiguration, Earth's surface became partitioned into biomes whose outlines remain familiar. The arrangement of grassland, forest, reef, and pollinator network emerged from dynamic processes rather than static design. These ecosystems, though modern in appearance, carry the imprint of climatic cooling, continental movement, and biological experimentation that defined the later chapters of the age. Above the steady turning of continents and oceans, another rhythm moved quietly through space. Earth did not circle the sun in perfect constancy. Its orbit stretched and relaxed over tens of thousands of years, shifting from more circular to more elliptical and back again. Its axis tilted slightly more, then slightly less, altering the angle at which sunlight reached the surface. Even the direction of that tilted axis traced a slow wobble, changing the timing of seasons relative to Earth's position along its orbit. These variations, subtle in any single year, accumulated across long intervals, adjusting the distribution of solar energy received at different latitudes. When summers in the northern hemisphere grew marginally cooler because of orbital configuration, winter snow sometimes persisted rather than melting completely. Snow reflects more sunlight than soil or forest, reinforcing local cooling. Over time, this feedback allowed ice to expand outward from high latitudes. Conversely, when orbital parameters favored stronger summer warmth, accumulated ice thinned and retreated. These cycles, known collectively as Milankovitch cycles, did not create ice ages alone, yet they paced the waxing and waning of ice sheets once global cooling had already lowered baseline temperatures. As Antarctic glaciation anchored a cooler world, northern hemisphere ice sheets began to develop more prominently. Vast glaciers spread across what is now Canada and extended into the northern United States. Ice advanced in lobes and domes, grinding bedrock beneath immense pressure, carving valleys and depositing moraines that would later shape lakes and river systems. Sea levels fell as water became stored within continental ice, exposing land bridges in some regions and altering coastlines elsewhere. These glacial intervals alternated with warmer interglacial periods during which ice retreated toward polar cores. Vegetation zones shifted in response, migrating southward during cold phases and northward during warmth. Animal populations adapted by moving, evolving, or, in some cases, diminishing. The pattern repeated across the Pleistocene, each cycle spanning tens of thousands of years, modulated by orbital forcing and amplified by feedbacks within the climate system. Deep ocean sediments preserve this oscillation in layered isotopic signatures. Ratios of oxygen isotopes in microscopic shells reflect changes in global ice volume and ocean temperature, creating a stratigraphic record of alternating cold and warm phases. Ice cores extracted from polar regions capture atmospheric composition and temperature proxies, revealing synchronized fluctuations across hemispheres. The onset of these recurring glacial cycles did not plunge the planet into uninterrupted cold. Instead, it introduced a pulse to the climate, a breathing between ice expansion and contraction. Landscapes were repeatedly reshaped, soils reworked, and ecosystems reorganized under advancing and retreating fronts. The ice ages began not as a singular event, but as a patterned interplay between orbital geometry, atmospheric composition, and the accumulating legacy of tectonic cooling that had prepared the stage for ice to claim and release the continents in measured succession. Across windswept plains where grasses bowed beneath persistent chill, immense silhouettes moved against horizons pale with dust and frost. The cold had settled into a recurring pattern, advancing and retreating with orbital rhythm, and in these oscillating landscapes, large bodies found both challenge and advantage. Among the most iconic were the mammoths, their curved tusks sweeping forward in elegant arcs, their thick coats layered with guard hairs and insulating underfur. Beneath skin lay substantial fat deposits that conserved heat, while small ears reduced surface area exposed to freezing air. Their molars, ridged and expansive, were suited to grinding coarse steppe vegetation that endured beneath snow and ice. In other regions, giant ground sloths roamed with deliberate strength. Some species reached heights that rivaled elephants when standing upright, using powerful claws to pull branches downward. Their massive frames supported extensive digestive systems capable of processing fibrous plants in environments where nutritional value fluctuated seasonally. Though not all inhabited the coldest zones, many adapted to cooler climates as forests shifted and open habitats expanded. Thick hides and substantial body mass helped buffer them against temperature extremes. The woolly rhinoceros carried its own suite of cold weather adaptations. Its broad, flattened horn may have been used to sweep aside snow in search of grasses. Dense fur and a robust build minimized heat loss, while shortened limbs reduced exposure to frigid winds. Fossil remains preserved in permafrost reveal intact hair and even stomach contents, offering detailed insight into diet and environment. These animals occupied vast stretches of Eurasian steppe, moving across landscapes shaped by glacial advance. Megafauna of this era benefited from large size in cold climates through principles consistent with thermoregulation. Greater body volume relative to surface area reduces heat loss, allowing massive animals to maintain stable internal temperatures with less metabolic strain. Many developed elongated limbs for migration across wide territories, tracking seasonal resources as ice sheets expanded and retreated. Social structures likely facilitated survival, with herds providing collective vigilance and cooperative defense. The ecosystems they inhabited, often described as mammoth steppe, were neither barren nor static. They supported diverse grasses, herbs, and shrubs adapted to dry, cold conditions. Predators, such as large felids and early wolves, followed herds across frozen ground, participating in dynamic food webs shaped by climate cycles. As glaciers advanced, ranges compressed. As ice withdrew, corridors reopened, allowing dispersal and genetic exchange. These giants embodied a convergence of evolutionary responses to recurring cold. Their anatomy, behavior, and distribution were intricately tied to the pulse of glacial intervals. For tens of thousands of years, they flourished within this patterned instability, their footprints pressed into soils that would later thaw, erode, and preserve traces of a world where immense mammals thrived under the long breath of ice. High in the layered canopy of warm forests, movement shifted from ground to branch. Among leaves filtering diffuse light, small mammals adapted to life above the forest floor began refining a different set of skills. Early primates emerged within these arboreal environments, where balance, depth perception, and precise coordination determined survival more than raw speed or strength. Their bodies remained modest in size, yet their anatomy hinted at a quiet departure from other mammalian lineages. Hands and feet evolved with flexible digits capable of curling securely around branches. Opposable thumbs and, in some species, opposable big toes increased stability during climbing and leaping. Nails replaced claws on many digits, broad and flat, enhancing tactile sensitivity rather than piercing bark. The pads of fingers grew more responsive, rich in nerve endings that conveyed texture and grip. In a world defined by vertical complexity, such refinements allowed controlled movement through a three-dimensional landscape of trunks, vines, and interlaced branches. Vision underwent parallel transformation. Eyes shifted gradually toward the front of the face, overlapping their fields of view to create stereoscopic depth perception. This binocular arrangement improved the ability to judge distances between branches, reducing missteps during leaps. The bony structure surrounding the eye deepened, offering protection and anchoring muscles that controlled fine movements. Color vision began to diversify in certain groups, enhancing the detection of ripe fruit and young leaves against a backdrop of green. These sensory and motor changes were accompanied by subtle enlargement of the brain, particularly in regions associated with vision and coordination. The neocortex expanded relative to body size, supporting more intricate processing of sensory input. Social behaviors likely intensified within these forest communities as communication through vocalizations, facial expressions, and grooming required cognitive flexibility. Memory of fruiting trees, seasonal patterns, and spatial routes through dense canopy may have provided selective advantages. Fossil evidence from regions of Africa, Asia, and North America preserves fragments of this ascent. Dental structures indicate diets rich in fruit and insects, while limb proportions reflect adaptation to climbing rather than sustained terrestrial running. Some early primates possessed elongated hind limbs suited to leaping, others retained more generalized forms. The diversification was gradual, yet it established a lineage that would later radiate into monkeys, apes, and eventually humans. The rise of primates did not dominate landscapes in the way megafauna once did. Instead, it unfolded within the shelter of foliage, guided by fine motor control and perceptual acuity. As climates fluctuated and forests expanded and contracted, these traits offered resilience. In branches swaying above forest floors, evolutionary pressures shaped hands capable of grasping and eyes capable of discerning depth, laying neural foundations that would influence the trajectory of the era in ways not yet visible within those early leaves. Dust began to settle where dense woodland had once held moisture and shade. Over long spans of time, shifts in ocean circulation and global cooling altered rainfall patterns across eastern Africa. Forest belts thinned and fractured, replaced in many regions by expanding savannas and open woodland mosaics. Seasonal drought intensified, and grasses advanced into spaces once dominated by continuous canopy. Rivers that had flowed through shaded corridors now cut across broader plains, their margins bordered by scattered trees rather than thick understory. Tectonic forces added further complexity. The gradual formation of the East African Rift elevated portions of the landscape, modifying wind patterns and creating rain shadows. Uplift altered drainage systems and contributed to regional drying. Lakes formed within rift valleys, fluctuating in size with climatic oscillations, recording in their sediments the alternation between wetter and drier intervals. These environmental changes did not occur in isolation, but intersected with the evolutionary trajectories of primates that had once thrived in forested habitats. As woodlands receded, primate populations encountered new selective pressures. Travel between tree clusters required crossing open ground more frequently. Food sources became patchier, demanding greater efficiency in movement and broader dietary flexibility. Some lineages remained within shrinking forest refugia, while others began adapting to more open terrain. Skeletal evidence from early hominins reveals subtle but significant changes in pelvis shape, femur angle, and spinal curvature. The foramen magnum, the opening at the base of the skull through which the spinal cord passes, shifted position in a manner consistent with a more upright posture. Bipedal locomotion emerged gradually rather than as a sudden transformation. Walking on two legs freed the hands, allowing carrying of food or offspring across exposed areas. An upright stance elevated the head, expanding the visual field above tall grasses. Energy expenditure during long-distance travel across savanna may have been reduced compared with quadrupedal knuckle walking under certain conditions. Fossilized footprints preserved in volcanic ash in East Africa demonstrate that by the time of early Australopithecus, habitual bipedalism had become established. These anatomical adjustments coexisted with retained arboreal capabilities. Early hominins still possessed curved finger bones and shoulder structures suited for climbing, suggesting a flexible lifestyle spanning both ground and tree. Brain size during these initial stages remained modest, yet neural organization continued to evolve in response to social complexity and environmental variability. Tool use, in its earliest forms, likely accompanied this transition, though direct evidence would become clearer in later species. Africa's changing climate did not dictate a single outcome, but created a landscape of opportunity and constraint. Within this shifting mosaic, primate ancestors navigated between forest remnants and open grasslands, their bodies responding to new demands. The gradual emergence of bipedalism reflected adaptation to a continent in transition, where drying air and widening horizons reshaped both terrain and lineage. Stone began to fracture with intention. Along river margins and open woodland edges in eastern Africa, flakes were struck from cores in deliberate motions that left sharp edges suited for cutting. These early tools, simple in appearance, marked a subtle threshold. They signaled minds capable of envisioning shape within raw material and hands steady enough to release it. The makers belonged to a lineage already walking upright across varied terrain, their bodies shaped by earlier shifts in climate and habitat. Australopithecus inhabited this transitional world for millions of years, combining upright gait with lingering arboreal traits. Their pelvis and lower limbs supported habitual bipedalism, while curved fingers and mobile shoulders retained climbing ability. Brain size remained modest compared with later species, yet dental patterns and jaw structure reflect diets flexible enough to include fruits, tubers, and possibly small animals. Fossil discoveries from sites such as Hadar and Laetoli reveal skeletons and footprints that capture both movement and posture, evidence of communities navigating landscapes that alternated between grassland and scattered woodland. From within this broader Australopith diversity emerged a species with a slightly larger cranial capacity and more refined tool association. Homo habilis, often regarded as one of the earliest members of the genus Homo, displayed changes in hand anatomy that improved precision grip. The thumb lengthened relative to fingers, and joint surfaces suggest enhanced dexterity. Stone artifacts attributed to this period commonly categorized within the Oldowan tradition, include flakes and choppers capable of processing meat and plant material with greater efficiency than unmodified stones. The use of tools introduced new dietary possibilities. Access to marrow and flesh from carcasses provided concentrated nutrients that may have supported gradual brain expansion. Although early Homo brains were still far smaller than those of modern humans, endocasts indicate incremental enlargement, particularly in regions associated with motor control and planning. Social cooperation likely intensified as well, with shared access to resources reinforcing group cohesion. These developments unfolded without abrupt transformation. Australopithecus and early Homo coexisted for extended intervals, and the boundary between them reflects gradual anatomical and behavioral shifts rather than sudden replacement. Climatic variability continued to influence habitat distribution, reinforcing selection for adaptability. The capacity to manipulate objects, transport food, and perhaps communicate with increasing nuance provided advantages in fluctuating environments. The first humans did not appear fully formed, but emerged through layered adjustments across generations. Upright posture, skilled hands, and expanding neural complexity converged in populations that began leaving clearer imprints in the archaeological record. Stone fragments scattered across ancient landscapes remain as quiet testimony to this transition, marking a point at which cognition began to shape matter in ways that would, over time, reshape the planet itself. Instability became the background condition rather than the exception. As ice sheets advanced and withdrew in response to orbital pacing, the climate system revealed a capacity for abrupt transitions layered upon slower trends. Temperature did not drift gently from one state to another. In some intervals, it shifted within centuries, even decades, altering rainfall, vegetation, and ocean currents with surprising speed. Ice core records from polar regions preserve these fluctuations in delicate bands of trapped air, where changes in greenhouse gas concentrations align with rapid warming and cooling episodes. Volcanic activity added further variability. Large eruptions injected ash and sulfur dioxide into the stratosphere, reflecting sunlight and temporarily lowering global temperatures. In other cases, sustained volcanic outgassing contributed carbon dioxide to the atmosphere, influencing longer-term warming. These geologic pulses intersected with orbital cycles and ocean circulation changes, creating a complex interplay that resisted equilibrium. The climate system oscillated across thresholds, amplifying minor perturbations into substantial regional shifts. Ice sheets, immense yet sensitive to temperature and ocean dynamics, occasionally destabilized. When warming penetrated their margins, meltwater accelerated flow toward the sea. Marine terminating glaciers fractured and released vast volumes of ice, raising sea levels and freshening surface waters. Such inputs disrupted thermohaline circulation, altering heat distribution across hemispheres. Evidence of these events appears in layers of ice-rafted debris within marine sediments, marking episodes when glaciers calved at heightened rates. For early human populations dispersed across Africa and later beyond, this variability imposed recurrent pressures. Habitats expanded and contracted, water sources shifted, and migratory corridors opened or closed. Genetic studies of modern humans indicate periods when population size narrowed dramatically, known as bottlenecks. These contractions may have coincided with severe climatic episodes, including prolonged droughts or volcanic winters that reduced available resources. Survival during such intervals required mobility, cooperation, and flexible subsistence strategies. The archaeological record reveals adaptations to this restless environment. Stone tool technologies diversified, with more refined flakes and prepared cores indicating planning depth and cognitive expansion. Control of fire, increasingly evident in later phases, offered warmth and protection against cold periods. Social networks likely extended across wider territories, facilitating exchange of knowledge and resources when local conditions deteriorated. Climate that would not remain calm became an evolutionary force in its own right. Rather than stabilizing after the onset of glacial cycles, the system displayed pulses of abrupt change superimposed on long-term cooling. These oscillations shaped landscapes and living communities alike, demanding resilience from species inhabiting them. In this context of continual fluctuation, early humans navigated an Earth whose atmosphere, ice, and oceans interacted in dynamic equilibrium, never fully settling, always adjusting to internal and external influences that rippled through the fabric of the era. Ash can travel farther than memory. In northern Sumatra, a volcanic system accumulated pressure beneath the crust until magma rose with force sufficient to fracture the surface on a continental scale. When the Toba supereruption occurred, it expelled vast volumes of ash and sulfur-rich gases into the atmosphere. Pyroclastic flows blanketed surrounding regions, and fine particles ascended high enough to disperse across much of the globe. Layers of volcanic ash preserved in South Asian sediments and distant marine cores testify to the magnitude of this event. Sulfur aerosols injected into the stratosphere likely reflected incoming sunlight, initiating a period of reduced surface temperatures, sometimes described as a volcanic winter. Estimates vary regarding the severity and duration of cooling, yet climatic models suggest that regional ecosystems would have faced substantial stress. Vegetation patterns may have shifted abruptly, rainfall altered, and food chains disrupted in ways that challenged both animals and early human populations. Genetic studies of modern humans reveal an intriguing pattern. Across diverse populations, overall genetic variation is relatively low compared with many other species. This observation has led some researchers to propose a population bottleneck, a period when human numbers declined sharply before recovering. One hypothesis links such a contraction to the environmental consequences of the Toba eruption, suggesting that only a small number of individuals survived in refugia where conditions remained tolerable. However, the evidence remains complex and debated. Archaeological sites in parts of Africa and India show signs of continued human occupation before and after the eruption, implying resilience rather than complete regional abandonment. Stone tool assemblages do not exhibit an obvious interruption in technological continuity. Some genetic models indicate that bottlenecks could have occurred at different times or resulted from cumulative climatic pressures rather than a single volcanic event. The story preserved in DNA and sediment does not align perfectly, leaving space for careful interpretation. What is clear is that human populations during the late Pleistocene were far smaller and more fragmented than today. Groups likely numbered in the tens of thousands globally, dispersed across varied habitats and connected by tenuous migratory routes. In such circumstances, any severe climatic disturbance could have narrowed numbers dramatically, even if not to the brink of total extinction. Survival would have depended on mobility, cooperation, and adaptability honed over previous cycles of instability. The possibility that humanity once contracted to a thin thread within a broader tapestry of life underscores the contingent nature of our presence. Whether the Toba eruption served as the primary catalyst or one of several contributing stresses, the episode illustrates how environmental volatility, intersected with a species still in its early expansion. From small, scattered communities, human populations eventually rebounded, carrying forward genetic signatures of contraction that echo faintly in the genomes of people living today. Beneath a shifting sky and advancing ice, the oceans absorbed change with immense but not infinite capacity. Cooling currents intensified as polar waters grew denser and sank more readily into the abyss, strengthening global overturning circulation. This redistribution of heat altered nutrient pathways, bringing cold, oxygen rich water into deeper basins while reshaping surface productivity. Marine ecosystems, sensitive to temperature and chemistry, adjusted in waves that mirrored climatic oscillations on land. Marine mammals responded first through migration and then through evolutionary refinement. Early whales, already fully committed to aquatic life, diversified into forms suited to colder seas. Baleen whales expanded their filter feeding capabilities, evolving elongated plates that enabled efficient harvesting of plankton blooms in nutrient-rich upwellings. Their immense body size, advantageous in retaining heat, also allowed long-distance migration between feeding and breeding grounds. Toothed whales refined echolocation further, navigating darker, deeper waters where prey distribution shifted with temperature gradients. Seals, sea lions, and walruses adapted to coastlines influenced by expanding seasonal ice. Thick layers of blubber insulated them against cold water, while modified limbs facilitated both swimming and hauling out onto shore or ice floes. In some regions, new ecological niches emerged as ice coverage created platforms for resting and breeding. The interplay between ice extent and marine mammal distribution became tightly linked, with population ranges expanding and contracting in response to glacial cycles. Sharks, ancient survivors of earlier eras, continued their own evolutionary adjustments. Modern lineages diversified during the Neogene, refining body plans optimized for speed and sensory acuity. Electroreceptive organs allowed detection of faint electrical signals emitted by prey, while streamlined forms enhanced efficiency in cooler, more stratified oceans. Some species thrived in productive coastal zones, others adapted to pelagic expanses where prey migrated seasonally. Their resilience across climatic transitions reflects flexibility in diet and habitat use. Marine life did not advance in a steady upward trajectory. Fossil records reveal intervals of collapse followed by recovery, often associated with abrupt climatic shifts or changes in sea level. When temperatures dropped rapidly or ocean chemistry altered, certain plankton communities declined, cascading through food webs. Yet recovery followed as new assemblages filled vacated niches. Coral reefs retreated during colder phases and re-expanded when warmth returned, though with changing species composition. Cooling ocean circulation intensified contrasts between regions, strengthening upwelling in some areas while reducing productivity in others. These variations influenced carbon storage and atmospheric exchange, linking marine processes to global climate feedbacks. Through cycles of stress and renewal, the oceans demonstrated both vulnerability and adaptability. Their immense volume buffered change, yet the fossil record preserves evidence that even the largest ecosystem on Earth operated under pressure, continuously reshaped by temperature, circulation, and the restless dynamics of the era. Shorelines began to resemble the outlines familiar today, not because motion had ceased, but because continental rearrangement slowed into configurations that would persist for millions of years. With the Isthmus of Panama fully established, North and South America stood joined, their combined landmass altering both atmospheric flow and ocean circulation. Mountain chains extended like vertebrae along western margins, while interior basins collected sediment eroded from rising peaks. The broad geometry of the Western Hemisphere approached a form that would shape climate patterns into the present. Across the Atlantic, Africa continued to adjust internally even as its external boundaries steadied. The East African rift system widened incrementally, a scar of extension where the crust thinned and fractured. Volcanoes punctuated the Rift Valley, and elongated lakes filled subsiding basins. Though continental breakup remained incomplete, the region signaled that tectonic forces still worked beneath seemingly settled terrain. Uplift along the rift altered regional rainfall and drainage, contributing to ecological diversity across eastern Africa. Elsewhere, plate boundaries maintained their subtle but relentless activity. The Pacific margin of the Americas remained a zone of subduction and uplift, feeding volcanic arcs and earthquakes. The collision of Africa with Eurasia continued to influence the Mediterranean region, compressing sediments and reshaping coastlines. Yet compared with earlier eras of rapid drift and ocean opening, the continents had reached relative stability in their broad arrangement. The major ocean basins, Atlantic and Pacific, retained their defining expanses, and polar positions of landmasses remained fixed enough to sustain persistent ice at high latitudes. This geographic stabilization reinforced climatic patterns that had emerged during preceding cooling. Ocean currents circulated along established routes, guided by continental barriers and seafloor topography. Monsoon systems strengthened where landmass configuration supported seasonal contrasts, and trade winds followed paths determined by the distribution of ocean and land. The interplay between tectonics and atmosphere continued, but within boundaries that had settled into recognizable form. Sedimentary records from coastal plains and continental shelves document this phase of relative equilibrium. River systems carved valleys that still guide modern waterways, depositing deltas that expanded outward into stable basins. Coral reefs fringed consistent shorelines in tropical regions, adjusting to sea level fluctuations, but within familiar geographic constraints. Mountain ranges that had risen earlier persisted as dominant features, influencing weather and biodiversity across adjacent regions. Though the planet never ceases its tectonic motion, the late Cenozoic witnessed continents occupying positions that frame today's maps. The choreography of plates slowed from dramatic rearrangement to measured adjustment. Within this framework, ecosystems and climates evolved under boundaries that would endure long enough to cradle the rise of complex human societies. Earth's surface, while dynamic beneath, presented a geography that felt steady on the scale of generations, even as deeper forces continued their quiet work. Bones began to vanish from the record with unsettling speed. In sediments dating to the close of the Pleistocene, the remains of mammoths, giant ground sloths, woolly rhinoceroses, and other large mammals grow abruptly scarce. Landscapes that had long supported immense herbivores and formidable predators shifted toward smaller-bodied communities. The disappearance did not occur uniformly across the globe, yet the pattern repeats on multiple continents within a relatively narrow span of time. Glacial cycles were already reshaping habitats, advancing and retreating with orbital rhythm. As the last great ice sheets began to withdraw, temperatures rose, vegetation zones migrated, and sea levels climbed. Grasslands contracted in some regions, forests expanded in others, and water availability fluctuated. For species adapted to cold steppe or specific migratory routes, These changes imposed severe stress. Populations fragmented as corridors narrowed, and genetic diversity likely declined under environmental strain. At the same time, anatomically modern humans expanded into new territories. Evidence of human arrival often coincides closely with megafaunal decline in regions such as Australia and the Americas. Archaeological sites reveal stone tools associated with large animal remains, suggesting hunting played a role. Even modest hunting pressure, when applied to species with slow reproductive rates, could have driven vulnerable populations toward collapse. The debate over relative influence remains active. Some researchers emphasize climate as the primary driver, noting prior glacial transitions that also altered ecosystems. Others highlight the unprecedented combination of climatic instability and a highly adaptable predator capable of cooperative hunting and landscape modification. The fossil record alone cannot assign singular cause. In certain areas, extinctions appear synchronous with abrupt warming events. In others, they follow soon after human settlement. It is possible that climate change weakened populations already near ecological limits, while human predation delivered additional pressure. Fire use by expanding human groups may have altered vegetation patterns, compounding stress on herbivores dependent on particular plant communities. Disease transmission has also been proposed, though direct evidence remains sparse. What is unmistakable is the scale of loss. Large mammals disappeared from continents where they had persisted through earlier climatic oscillations. Entire ecological roles vanished with them. Without mammoths to trample and graze, grassland structure changed. Predators, dependent on large prey, declined or adapted to smaller targets. Nutrient cycling patterns shifted as the biomass of megafauna diminished. The world that emerged from this transition bore the imprint of absence. Smaller mammals, birds, and humans occupied landscapes once defined by towering herbivores and powerful carnivores. The late Pleistocene extinctions marked the end of an age of giants, closing a chapter that had begun with vast bodies moving across glacial plains. In their disappearance, the balance of ecosystems recalibrated, leaving behind a quieter horizon shaped by forces both climatic and human in origin. Water began to move with quiet persistence. As the last glacial maximum loosened its hold, ice sheets that had pressed across northern continents thinned and retreated. Sunlight lingered longer over exposed ground, and seasonal warmth extended its reach. Vast walls of ice withdrew toward higher latitudes, releasing meltwater that flowed through braided channels and proglacial lakes before entering the oceans. The retreat unfolded over thousands of years, yet in geological terms it marked a swift transition from deep cold to a more temperate world. As continental ice diminished, global sea levels rose by roughly 120 meters. Shorelines that had stretched far beyond present coasts were gradually submerged. River valleys flooded, transforming into estuaries and bays. Low-lying plains disappeared beneath advancing tides, and islands emerged where hilltops once stood within broader landscapes. The reshaping of coastlines altered ocean currents locally and redefined habitats for both marine and terrestrial species. Sediment cores and coral terraces record this steady rise in sea level. Coral reefs, which grow near the surface of warm water, preserved stepped sequences that trace upward migration as oceans deepened. Each terrace marks a pause or slowing in the rate of rise, capturing the complex interplay between melting ice sheets and climatic stabilization. Meltwater pulses, episodes of accelerated discharge from collapsing ice margins, briefly hastened the ascent of seas, before settling into slower increments. On land, vegetation zones migrated in response to warming temperatures. Tundra retreated poleward, replaced by expanding forests, and grasslands adapted to milder conditions. Lakes formed in depressions carved by glaciers, filling with fresh water and supporting new ecosystems. Animal populations shifted accordingly, tracking changing resources and adjusting to emerging habitats. The disappearance of massive ice sheets also relieved pressure on underlying crust, initiating gradual isostatic rebound that continues in some regions today. Atmospheric circulation patterns stabilized into configurations recognizable in the modern era. The strengthening of ocean currents, combined with reduced ice cover, established a climate regime that, while still variable, lacked the extreme glacial reach of preceding millennia. This interval, known as the Holocene, provided relative warmth and consistency that would later support the development of agriculture and permanent settlements. The final retreat of ice did not erase the memory of cold, but it marked the beginning of a climatic baseline distinct from the glacial cycles that dominated much of the preceding epoch. Sea levels settled near their current position, coastlines assumed familiar contours, and ecosystems reorganized within a warmer framework. In the wake of melting ice, Earth entered a phase that feels stable by human standards, even though it rests upon the same dynamic systems that have shaped the entire era. Air began to arrange itself into pathways that would circle the planet with dependable force. As ice sheets retreated and sea levels approached their modern position, the contrast between equator and pole sharpened into patterns that guided atmospheric flow. High above the surface, narrow bands of fast-moving air consolidated along temperature gradients, forming the jet streams. These currents, shaped by Earth's rotation and differential heating, steered storm systems across continents, influencing where rain would fall and where dryness would persist. Over the Atlantic, warm surface water traveled northward in a steady ribbon, releasing heat into higher latitudes before cooling and sinking. This circulation, often referred to as the Gulf Stream and its northern extensions, stabilized within the broader thermohaline system that had strengthened during earlier cooling phases. By transporting warmth toward Europe and moderating regional climates, it became a defining feature of post-glacial weather. Fluctuations occurred, yet the overall structure endured, anchoring a distribution of temperature that shaped vegetation belts and seasonal rhythms. Across South Asia and parts of Africa, monsoon systems intensified under the combined influence of continental configuration and differential heating between land and sea. During warm months, heated land masses drew moist air inward from surrounding oceans, producing seasonal rains that nourished river systems and supported dense populations of plants and animals. In cooler months, circulation reversed, ushering in drier air. These oscillations, though ancient in origin, settled into patterns recognizable in the modern era, reinforced by established mountain ranges and ocean currents. Climate zones emerged with clearer boundaries. Tropical regions near the equator experienced relatively consistent warmth and periodic rainfall shaped by the intertropical convergence zone. Subtropical belts, influenced by descending air from Hadley cells, developed arid conditions that gave rise to deserts. Mid-latitude zones encountered alternating high and low pressure systems carried by the jet streams, producing variable weather and pronounced seasons. Polar regions retained colder conditions under persistent ice and reduced solar input. The arrangement of continents and oceans during this interval provided the scaffolding for these atmospheric systems. Mountain ranges deflected winds and created rain shadows, while ocean basins stored and redistributed heat. Vegetation patterns reinforced climate through evapotranspiration and albedo effects, creating feedback loops that stabilized regional conditions. Although variability persisted through shorter term oscillations, the overarching framework of modern weather had taken shape. Within this structured atmosphere, human societies would later learn to anticipate seasonal changes, plant crops, and navigate seas. The era did not eliminate dynamism, yet it established recognizable regimes of wind and rain that continue to define daily life. The choreography of jet streams, ocean currents, and monsoon cycles became an enduring feature of the planet, a legacy of tectonic movement and climatic adjustment that quietly built the weather patterns now considered familiar. Stability, when examined closely, dissolves into oscillation. Beneath the appearance of settled coastlines and familiar wind patterns, the climate record reveals persistent variability layered across millennia. Ice cores drilled from Greenland and Antarctica preserve delicate cylinders of compacted snowfall, each annual layer trapping tiny bubbles of ancient atmosphere. Within those bubbles lie measurements of carbon dioxide and methane that rise and fall in repeating arcs, closely aligned with shifts in temperature inferred from isotopic composition. The story they tell is not of constancy, but of continual adjustment. During glacial intervals, atmospheric carbon dioxide concentrations declined, reinforcing cooling already initiated by orbital geometry and feedbacks from expanding ice. In warmer interglacials, carbon dioxide increased, amplifying rising temperatures. These fluctuations were neither trivial nor uniform. Differences of only a few tens of parts per million corresponded with sweeping transformations of vegetation, sea level, and ocean circulation. The climate system responded to small chemical variations with disproportionate ecological consequence. Temperature variability data from marine sediments complement the ice core archive. Ratios of oxygen isotopes within the shells of microscopic organisms chart repeated cycles of cooling and warming extending back millions of years. Each oscillation marks a reorganization of ecosystems on land and sea. Grasslands expanded during colder, drier phases, while forests reclaimed territory during warmer intervals. Deserts shifted their boundaries. Lakes formed and vanished in response to rainfall patterns that oscillated with atmospheric circulation. Ecological communities rarely remained static for long. Species migrated in response to advancing ice or encroaching drought, altering competitive relationships and gene flow. Coral reefs retreated during cooler phases and re-established during warmth, often with new species compositions. Large mammals adapted or disappeared as habitats transformed. Even within the relatively brief span of the Holocene, regional climates have experienced episodes such as the Younger Dryas, a rapid return to colder conditions before resumption of warming. The illusion of permanence arises from the human scale of perception, yet geological archives demonstrate that the Cenozoic Era was characterized by recurring perturbation. Carbon cycles fluctuated in concert with tectonic uplift, volcanic emissions, and biological feedbacks. Ocean currents strengthened or weakened in response to freshwater inputs and temperature gradients. Ice sheets advanced and retreated in patterned rhythm, leaving moraines and glacial polish as evidence of their passage. Through these repeated reshaping events, life endured by adapting to shifting baselines rather than relying on fixed equilibrium. The era that produced familiar climates did so through variability, not through stasis. Beneath apparent calm lay a dynamic interplay of chemistry, circulation, and orbital mechanics, ensuring that the world remained responsive to subtle forces. The Cenozoic was never a settled stage, but a continuous negotiation between stability and change, recorded in ice, stone, and living genomes. Long before cities and agriculture, the conditions that would favor our species were assembling piece by piece across open ground and shifting skies. Expanding grasslands did more than reorganize ecosystems. They altered the demands placed on bodies moving through them. In these broad landscapes, where prey traveled across distance and shade was sparse, endurance became an advantage. Anatomical features that had emerged gradually, elongated lower limbs, arched feet, elastic tendons, and the ability to regulate heat through sweating, allowed sustained movement under the sun. Persistence hunting, in which prey is followed over long distances until exhausted, became possible within this terrain. The structure of savannas favored stamina over bursts of speed, quietly shaping physiology toward efficiency in prolonged effort. Climate variability reinforced this trajectory. Across the late Cenozoic, alternating wet and dry intervals rearranged water sources and vegetation zones. Populations that endured were those capable of flexibility, able to adjust diet, migration routes, and social organization as conditions shifted. Variability selected not for specialization alone, but for behavioral plasticity. Groups that could remember distant watering sites, anticipate seasonal changes, and innovate in response to scarcity carried advantages into subsequent generations. Within this context, brain expansion offered cumulative benefit. Enlarged cortical regions supported more complex planning, communication, and tool use. The energetic cost of maintaining a larger brain was substantial, yet it was offset by improved access to calorie-dense foods, cooperative hunting, and food sharing. Neural development enhanced the capacity to model future scenarios, strengthening survival in environments where predictability was limited. Cognitive growth did not unfold in isolation. It intertwined with dietary shifts, social structure, and technological refinement. Cooperation under stress became a defining feature. In fluctuating climates, solitary survival carried higher risk than coordinated effort. Sharing food buffered short-term shortages. Collective child-rearing increased offspring survival. Communication through gesture and eventually language deepened bonds within groups, transmitting knowledge across generations. Under repeated environmental pressures, social cohesion became as critical as physical endurance. The Cenozoic provided not a single stable cradle, but a series of challenges that rewarded adaptability. Grasslands opened horizons that favored long-distance travel. Climate oscillations demanded innovation. Brain enlargement amplified foresight and memory. Cooperation multiplied individual strengths within collective networks. Each element alone would have been insufficient. Together, they formed a web of traits uniquely suited to a world defined by change. By the time anatomically modern humans emerged, the groundwork had been laid by millions of years of tectonic uplift, climatic fluctuation, and ecological restructuring. The era shaped bodies capable of endurance, minds capable of abstraction, and societies capable of resilience. Humanity did not arise in spite of instability, but within it, molded by the same dynamic forces that had sculpted mountains, oceans, and weather throughout the long unfolding of the age. The ground beneath modern cities rests upon layers formed within the same era that began after the last dinosaurs vanished. The Cenozoic has not concluded. It continues quietly beneath highways, forests, and shorelines. Its tectonic motions persist, its climate system remains active, and its cycles have not reached a final resolution. What feels contemporary is, in geological perspective, the most recent phase of a long unfolding chapter. The present interval, known as the Holocene, represents a brief interglacial within a broader pattern of glacial oscillations. Following the retreat of the last major ice sheets, temperatures stabilized at levels warmer than those of the preceding glacial maximum. Ice retreated toward polar cores, sea levels approached their current heights, and ecosystems reorganized under relatively consistent conditions. This stability, though modest on geological timescales, allowed agriculture, settlement, and the rise of complex societies. Yet the Holocene is only a thin band within sedimentary archives, a fleeting warmth between longer cycles of cold. In recent centuries, human activity has introduced a new influence upon atmospheric composition and planetary systems. The concentration of carbon dioxide has risen beyond the range observed in earlier Holocene records, driven by combustion of fossil fuels and land use change. This has led some scientists to propose that a new epoch, often termed the Anthropocene, should be recognized to reflect the scale of human impact on geology and climate. The debate continues within scientific communities, centering on whether human-driven changes warrant formal stratigraphic distinction or remain part of the ongoing Cenozoic framework. Regardless of nomenclature, the underlying mechanics of orbital variation persist. Earth's tilt, orbit, and axial wobble continue their slow cycles, influencing the distribution of solar energy. In the absence of significant human alteration, models suggest that glacial conditions would eventually reassert themselves as orbital configurations favor cooler summers in high northern latitudes. Ice age cycles are not relics of the past, but components of an enduring climatic rhythm. The timing of their return, however, may be modified by elevated greenhouse gas concentrations. Thus, the Cenozoic remains an active narrative rather than a concluded one. Its glaciers have advanced and withdrawn repeatedly. Its continents have shifted incrementally. Its ecosystems have adapted to persistent change. Humanity occupies only the latest fraction of this era, influencing processes that once seemed governed solely by tectonics and orbit. The chapter continues to unfold, shaped by forces both ancient and newly intensified, within the same dynamic framework that has guided the planet since the first recovery from extinction. In museums and films, towering reptiles hold the spotlight, their silhouettes fixed against volcanic skies and ancient swamps. Their age feels distant and dramatic, stamped deeply into imagination. Yet the ground outside the museum doors, the hills beyond the parking lot, the coastline tracing the horizon, belong to a far longer and more intricate chapter. The era that followed the reptiles did not merely inherit a scarred planet, it rebuilt it, altered it, and continues to guide its rhythms. During this span, mountains rose where seas once rested, and entire ocean gateways opened and closed as continents drifted into new alignments. Ice sheets advanced and withdrew across hemispheres, carving valleys and redirecting rivers. Grasslands expanded, forests reorganized, coral reefs assembled intricate limestone architectures beneath clear water. Mammals diversified into forms that filled land and sea, from the largest whales to the smallest primates clinging to branches. Climate oscillated repeatedly, never settling for long, nudging ecosystems into new configurations again and again. This was not a gentle aftermath. Carbon surged into the atmosphere during intense warming intervals. Later, vast uplifts and altered currents drew it down. Polar regions shifted from forested warmth to frozen expanse. Sea levels climbed and fell by dramatic margins. Entire faunas appeared, flourished, and vanished. The Cenozoic unfolded as a sequence of transformations, each phase layered atop the previous one, shaping terrain and life with persistent force. The landscapes that feel familiar today are products of that long instability. The pattern of winds that sweep across continents, the currents that circulate through modern oceans, the alternating belts of desert, forest, and savanna, all emerged through processes that refine themselves over millions of years. Even the soils beneath cultivated fields were ground and redistributed by glaciers that once covered broad portions of the northern continents. River systems found their modern courses as uplift and erosion worked in balance. The scenery framed by windows, whether urban or rural, carries the imprint of tectonics, climate shifts, and biological innovation woven together through time. It is easy to imagine permanence when mountains appear immovable and shorelines seem fixed. Yet this era demonstrates that stability is often temporary. Glacial cycles reshaped coastlines within spans far shorter than continental drift. Ecosystems reorganized under pressure from cooling and warming alike. Species adapted, migrated, or disappeared as conditions shifted. Humanity arose within this flux, inheriting a world already shaped by repeated change and now contributing to that trajectory. The Cenozoic does not end with a dramatic curtain. It continues beneath our steps, within atmospheric currents, within the slow creep of plates, and the quiet persistence of ice at the poles. The age of mammals, of grasslands, of complex climates remains in motion. The planet outside appears steady, yet it is part of an unfinished story, still being written by forces that have never truly rested.